We're going to start on Chapter 8. Chapter 8 deals with chemical reactions. We're also going to do Chapter 9. Chapter 9 deals with chemical change. Chemical reactions, chemical change, same thing. In a chemical change, what happens is you start off with substances, you have the atoms rearranged, that is, those substances get consumed in the sense that the atoms get rearranged to form new substances, which we call the products. And so chemical change, chemical reactions, so 2 chapters worth of chemical reactions. But it's not really 2 chapters worth, it's much more than 2 chapters worth, because chemical properties are an important topic, and so there's additional supplemental material in the lab manual. And so if you take a look at the lab manual, we'll see a section on reactions here. Simplified solubility rules, activity theory, reactivity metals, chemical equations. So 6 pages there. And then oxidation numbers. This is related to chemical properties and chemical change. A couple of pages there. Concentration problems, no. But net ionic equations, yes. 4 pages there. Relative strengths of acids and bases, yes. We're going to be talking about these next section. Answers to supplementary problems, no. But this, Chem Compact B, chemical reactions. Chem Compact B is some chapter that was written. It's going to be 93 to 116. Over 20 pages there. And then Chem Compact G goes from 117 to 141, so about 50 pages plus the 60 pages, so more than 60 pages of material that will be found in the supplement. And so we're going to do chapters 8 and 9 plus all this stuff in the supplement here. And so what I'm going to do is, I don't like the way it's organized. I don't like the way it's organized in the supplement for the chapters. So I'm going to present it differently. And so then I'm going to present it differently. It's going to be hard to follow along in the book. Or the PowerPoints. So I apologize in advance for that. Otherwise, you have to memorize a lot more reaction types. The number of reaction types that you have to memorize as presented are 12, so, or more. So we're going to do it differently. All right, so we'll just start off. So this particular section is critical that you take some notes, so you can follow along. Otherwise, once you get lost, it's going to get very confusing. But evidence of chemical change. So when we look at a chemical reaction or a chemical change, we're looking for things, visual clues or property clues or something like that, that there was some kind of chemical change versus a physical change. And so a change of color, is that chemical or physical? Now, it could be either. For example, if you dilute, if I take this soap here and dilute it with water, the color changes, it lightens, right? So we have to be careful. Sometimes the change of color might be physical, sometimes it might be chemicals. We just look at it carefully and see. Formation of a solid product, is that always chemical or could that be physical too? It could be physical. So for example, if you take tap water and evaporate all the water, do you know what's going to happen? You're going to be left with a solid residue. All the minerals will form as a solid at the bottom of the cup or whatever you're using. And so formation of a solid might be physical, might be chemical. You have to look at it. Formation of gas, if you boil water, is boiling water physical or chemical? Physical. Absorption or release of heat. This might be physical as well. Hot objects, do they release heat? Hot objects? Hot objects release heat. Cold objects, do they absorb heat? Is that a chemical or is that a physical? It could be just physical. Hot object cools down. So if you take your hot coffee and it becomes cold coffee, was that a chemical change or a physical change? It's a physical change. So all these, all these we could list as characteristics or evidence of physical change as well. So, what we have to do is we have to look at these individually and then see. How about emission of light? Is that physical or chemical change? Like the light bulb. When you have a light bulb and it emits light, then does the tungsten inside there change physically or chemically? That is, once it emits the light, is it still tungsten or did it change to something else? Like maybe... It's still tungsten, yeah. It's still tungsten. In fact, they don't want it to change. That's why in light bulbs, the old incandescent light bulbs, they put in an anaerobic environment. Anaerobic means what? Anaerobic means no oxygen, right? Is if there's oxygen, if air gets inside that light bulb, do you know what happens to the tungsten? It'll undergo chemical change, screw up the light bulb. Is when tungsten becomes oxidized, it forms tungsten oxide. Tungsten oxide is very brittle and it cracks and breaks. Whereas tungsten metal is more soft and malleable. And so all these can be evidence of physical changes as well. So just because it's on this list doesn't mean it's a chemical change. We look at specific examples here. And so this is evidence of a color change not due to dilution. There's a stopwatch. This is a color change due to a chemical. This has got to be chemical because look at the color. It starts off pretty dark and then lightens over time. And so what this means is that we're losing we're losing the substance that's giving off the color here, causing it. And so this would be an example of a chemical. We aren't diluting it. If we were adding more water, of course the color is going to fade. But since we aren't adding more water, I suspect this is a This is the formation of a solid. Is this a chemical or physical? So a drop hits and clouds up. You see how the cloud forms here? That cloud consists of tiny crystals of solid. We call this a precipitate. So when we have precipitate like this forming, this has got to be a chemical. This is not evaporating all the water and being left with a solid residue of minerals. This is a chemical change here. So this is called precipitation. Is this a chemical or physical? If we boil water, we're going to form a gas, steam. However, if you drop an Alka-Seltzer tablet in here, it forms a gas. Is this a chemical change or physical? This is a chemical change in this case. There wasn't gas that was trapped in the Alka-Seltzer, waiting to be released. This is gas being formed by the reaction of the Alka-Seltzer. This is called effervescence. Effervescence. This is evolution of heat and light. In this case, do you see like a tungsten rod heating up or tungsten bar heating? No, in this case it's different. This is going to be a chemical change. It's like the Bunsen burner. It would be a chemical change. In fact, this is a Bunsen burner. How about this? Are these just hot objects giving off light? No. This is chemical luminescence. How about this? This is a cold compress. You squeeze it and break something inside. Pack it, mix it, shake it up. this whole thing gets cold. When something gets cold, that means it's taking away heat from you or whatever else is in contact with it. And so if something absorbs heat, we call it what? Endothermic. If something releases heat, we would call it exothermic. And so this one is endothermic. Whatever the process is, it's absorbing heat. Is that physical or chemical? In this case, it's physical. There was some salt in here. When the salt dissolves, it absorbs some heat. It could potentially be chemical as well. It doesn't have to be physical. So there are examples of chemical processes. Temperature can change. We could have heat transfer, but not given here. Okay, here we have sodium reacting with water. Sodium. Water. They put a dye in water. You can't see the dye here. You can see the dye after the reaction started here. But when the sodium goes in the water, you can see it. There's a little molten ball of sodium. A lot of heat's generated. And so when the sodium comes into contact with water, heat's generated. It gets hot. We call that type of process endothermic or exothermic. This would be exothermic. So heat is released. It gets hot. It doesn't take much heat to melt sodium. Sodium melts at about 90 degrees Celsius. Reacts like this. If you have a lot of sodium, this will catch on fire. And if you have a, did I show you the sodium disposal? No? Like, excuse me, this, sodium versus sodium ion. Now both are made of the same element, the element sodium, but one has a charge, the other doesn't have a charge. Which one is more stable? And they say, you know, they say this is, our book says this is Dr. Jekyll and Mr. Hyde. And so which of these are the more stable, Dr. Jekyll or Mr. Hyde? Dr. Jekyll? Dr. Jekyll, so which one of these is the Dr. Jekyll of sodium, the stable form? The one with the neutral, or the one with the positive? So in other words, if somebody's saying you need to cut the sodium out of your diet, are they talking about sodium metal or are they talking about sodium ion? Sodium metal? Well, let's take a look. Maybe, you know, because we don't know. And so probably the best thing to do is just to memorize some information about sodium. And so let's take a look at this. There was some sodium surplus. This was by the Army. I think that was. Yeah. Disposal of surplus sodium. This is not sodium ion that they're disposing. This is sodium metal that they're disposing of. We'll take a look. Share this around.
20,000 pounds of highly dangerous metallic sodium head for destruction in Lake Lenore, Washington. The government surplus chemical ignites and explodes when wet. The alkali lake is devoid of fish and forms an admirable disposal spot. A 3,500-pound container of sodium hurtles into the lake and crashes through a foot of ice. As the water seeps in, smoke rises through a series of muffled explosions. The acrid clouds billow several thousand feet over the steep sides of the lake. Disposal of the chemical by the War Assets Administration is made necessary because no public carrier will accept it for transportation to a purchaser. One after another, with varying effects, the containers go up with spectacular results as water and sodium meet. A once lethal war chemical becomes a peacetime pyrotechnic display.
Fortunately, this reaction is not as violent. It is much less sodium. That was 3,500 pound drum of sodium. This is just a small piece of sodium. It still could ignite and still could potentially explode. And depends. But anyway, which one is more stable? Sodium metal or sodium ion?
That's not.
Sodium ion. And so the stable form of sodium is sodium ion. The unstable form would be sodium metal. Same element. And so it's just the charge. You know, the charge dictates the difference. It's like, what's the stable charge on chlorine? You know, what's a good happy charge on chlorine? -1. What's a very unhappy charge on chlorine? +7. Very unhappy charge. And so it's the same element, it's chlorine, but the charge makes a world of difference in its behavior. And this is why in chemistry, chemists are most interested in what? In charge. And if they're most interested in charge, then they're most interested in what force of nature? Gravity? Well, chemical forces, yeah, but what are chemical forces? Are they electrical, you know? So this is why on the test I asked the exact same question. In fact, I ask the exact same question every semester. You know, what force is most important in chemistry? Because it's a very important question, right? And everybody should know that, no matter what. Even if I already asked it, I'm going to ask it again and again. And so the charge makes a huge difference. Whether there's no charge or a positive charge makes a huge difference, like this, even though it's the same element.
Does that mean, like, even though it's neutral, doesn't mean it's more stable than...
No. Just because it's neutral doesn't... In certain ways, yes. In certain ways, neutral is better because we want things electrically neutral. If you build up too much charge, you're going to build up too much what we call voltage and static electricity, and it makes it unstable. And so there's more to it than this. But for behavior here, at least initially, you know, normally a lot of people think neutral is good, but you know, if we're comparing chloride versus chlorine, is neutral really good? You know, what would you rather sprinkle on French fries? You know, although it'd be hard, yellow, green chlorine gas or sodium chloride, salt? No, salt. Now, if you try to buy, you know, I'm on a low sodium diet. So I want to buy salt without the sodium. And so I'm going to just buy the chloride, and they can keep the sodium, you know. I'll pay the same price for it because it's okay if I don't get the sodium. I don't want the sodium. You can have it. I'll pay the same price for it, but you know what? I wouldn't be able to buy it. You can't buy it. You know why? Because it would be too unstable. You have to have the cation and the anion. I can't just go and get a salt shaker just full of chloride, cut the sodium. That's one way to cut the sodium out of your diet, right? You can't do that. And so in that sense, neutral is more stable. But when we're looking at reactivity of elements, then we're just looking, you know, this is neutral, this is positive. This is much more reactive. Look at, when you put sodium ions in water, do you get an explosion like that on the video? You know, if they dump 3,500 pounds of salt in Lake Lenoir, Washington, are they going to get a big explosion like that? No. And so, that's it. And so when we're doing that, yes, we're comparing that, but there's a little bit more to the story than what I'm telling you. But the easiest thing to do is say, yes, this is happy, this is unhappy. Just like this. Chloride, this is happy, this is chlorine. Is it happy? No, it's not happy. This is very reactive. It's unstable. You know, if you filled your room up with chlorine, you would be pretty miserable. Because chlorine is not happy. It's going to start attacking. So charge is very important. We'll always pay attention to the charge. This is why it drives me crazy. When people write the formulas for ions and don't bother writing the charge, it drives me crazy. It drives me crazy because, like, if I ask what is the formula for sodium ion and they write Na, not Na plus, it's huge. You know, it's a huge mistake. Huge mistake. Well, what happens when you take sodium and combine it with water? Now, this is what happens. If we take sodium, sodium is, what does the S represent here? Sodium solid. Mix it with water. Water is L for liquid. You know what it forms? It forms hydrogen. Hydrogen gas. Is hydrogen gas stable or unstable? Like, okay, I said you don't want to fill up your room with chlorine gas, but would you want to fill up your room with hydrogen gas? No. And so it's relatively unstable. And this is what causes the explosions. What causes the explosions is the ignition of hydrogen gas in the presence of, what else do you need? Hydrogen and oxygen. And so if they dump this in a anaerobic environment, there would be no explosion. You need some oxygen in there. Air, in other words. And then it forms this. What's this called?
Sodium hydroxide.
Good, sodium hydroxide. AQ stands for? And this is heat. Oftentimes we don't show the heat. Is this endothermic or exothermic? This is exothermic. If the heat is hot enough, it'll ignite the hydrogen if the heat is hot enough. And so it depends on how fast this reacts. If this reacts slowly and the heat is dissipated slowly, in fact, like in the test tube here, the heat could be dissipated slowly, the hydrogen won't ignite because it needs to get hot enough, what we call the flash point, before it ignites. Well, this is called a chemical reaction or chemical equation. In a chemical equation, the atoms are just rearranged. So we start off with these. These are called the reactants. And we end up with these, the product. And so what happens here is we go from sodium, okay, here to sodium and sodium hydroxide. Oh, wait a minute. Maybe nothing happened to hydrogen. It starts off as H2 here, and it ends up as H2 here. Is that correct? Hydrogen stays the same because we started off with H2, we end up with H2. Is that right? No, that's not exactly right because this H2 is not a hydrogen is there hydrogen gas in water? Is there hydrogen gas stuck on oxygen atoms in water and just got to shake this up and then the hydrogen gas will come off as H2? No, these are hydrogen atoms. It just so happens I have two hydrogen atoms bond to one oxygen. This is hydrogen gas, which is totally different. Explosive? Is water very explosive? No. We got that. But when I look at this, you know, I have one sodium here, two hydrogens here, but when I look at this, I have two hydrogens here, but I have a third one here. So I'm going from two hydrogens to three hydrogens. What happened there? What happened there, we just add atoms as needed to either side? No. So what we say is this equation is unbalanced. And so what we need to do is this. We need to balance the equation. The way we balance equations is by changing the coefficients. So one easy way of balancing this, I'll tell you the easiest way of balancing this for me. The easiest way for balancing this is just go sodium solid plus H3O liquid. This is going to yield H2 plus NaOH. H2 is a gas and NaOH is AQ. Now I got 3 hydrogens because I just changed this to H3O, that's 3 hydrogens, right? And so I have 3 hydrogen atoms here, and then 2 of those are going to end up in hydrogen, 1 of them is going to end up in hydroxide. Is that the way to balance this? No, we never change the subscript, because if you change the subscript, that means that, what is H3O anyway? Well, that's not water. Well, so why don't I just add an H? If I add an H here, then I have 3 hydrogens. But did we have any H there to begin with? No. Can't do that. So the only thing I can do is change the coefficients. Well, to change the coefficients there, I got 1 sodium there, sodium. I need 3 hydrogens. So one way of doing this is just doubling the sodium. We'll double the water and double the sodium hydroxide. So this should work. This is what we have here. So we have 2 sodium atoms there, and then 2 times 2 is 4 hydrogens. So I'll have 2 hydrogens here, and then 2 times 1 is 2, so 4 hydrogens here. And then 2 oxygen atoms. And we have 2 oxygen atoms here. So now we have all these atoms that were present here just being rearranged to form new products there, new substances. So this is a big example of chemical change, and this is how we balance it. And so let's get some practice with balancing chemical equations by changing the coefficient. So we talked about this solid, liquid, gas, and AQ. Aqueous means dissolved in water. Well, let me skip this stuff here. This is the procedure for balancing it. I'm going to go through all this. But I'm going to jump a little bit. To there. Now, excuse me, there are two ways of looking at this particular equation. We're going to come back to this equation later. We're going to look at it in this equation here first. And so here's a balancing exercise. Balance the equation for the reaction of solid phosphorus pentachloride with liquid water. So what is solid phosphorus pentachloride? What's the formula for that? Yeah, good. PCl5, it's a solid, so we'll write S. Reacting with liquid water, it's H2O liquid. Okay, yielding. This arrow means yields or forms. And so they're going to tell us what it forms. It's going to form phosphoric acid. What's the formula for phosphoric acid? H3PO4 is correct. Phosphoric acid is a very common acid. So you should be able to tell me that one quickly. And then hydrochloric acid. What's the formula for hydrochloric acid? HCl. And that's also a very common acid. It says solutions. So these are aqueous solutions. So this is AQ here, this is AQ here. Okay. Now we have to balance it. When I balance it, you try to save the simplest ones for last, like either the water or the HCl. Those are 2 elements, whereas 4 PCl5, but this is a 3. So let's balance phosphorus first. Phosphorus is already balanced. So you see I have 1 phosphorus atom here, ignoring the chlorines, and I have 1 phosphorus atom here. So it's balanced. Then let's balance the chlorines. I have how many chlorine atoms here? 5. And I only have 1 here. So I'm going to change it by changing the coefficient. So now I'm going to have 5 HCl. And so that balances the phosphorus and chlorine. And so I do not want to touch the 1st, 3rd, and 5th. Because if I change any of these, then it's going to ruin the balance that I just set up. And so I'm just going to adjust this one. So what we're going to do is we're going to look at the, let's look at the hydrogens next. So I have 3 hydrogens here and 5 hydrogens. So that gives me a total of 8 hydrogens here. And I don't want to change that, because if I change either of these, then it screws up what I just balanced. So the 8 hydrogens, I'm going to change it on this one because we messed it with it yet. And so how do I get 8 hydrogens out of this? I need to change the coefficient to 4. So 4 times 2, that gives me 8 hydrogens. And this is going to fix the number of oxygens. Now I got 4 oxygens here, and fortunately I have 4 oxygens here. And so we say that this is balanced now. Balance just means, you know, atoms were neither created nor destroyed. All right, when we interpret chemical equations, we can look at things at the particulate level or at the macroscopic level. At the particulate level, we're looking at individual molecules. So if I take 2 molecules of hydrogen and 1 molecule of oxygen, this is going to form 2 molecules of water. Is this an exothermic or endothermic reaction? Can you tell? They don't write heat here. If they wrote heat over here, plus heat, this would be exothermic because heat would be a product. If they wrote heat on the left side, heat would be a reactant, so it would be endothermic. Heat would be consumed, just like the other reactants in the formation of the products. But even though they don't specify, you should be able to tell if it's endothermic or exothermic. Is it endothermic or exothermic? Endothermic? How can you tell? Well, the way I can tell is by looking at this. Which one is higher energy, less stable? A mixture of hydrogen and oxygen or water? Hydrogen and oxygen are high energy, potential energy I'm talking about, less stable. Water is low energy, more stable. So if I'm going from high energy to low energy, and energy can neither be created nor destroyed, what happens to all that extra energy? All that extra energy must be given off as heat in this case. And so it's got to be plus heat. It's going to be exothermic. And so we could look at this at the particulate level, but we could also look at it at the macroscopic level. It doesn't have to be individual molecules, like 2 molecules of hydrogen. It could be like 2 dozen. If I had 2 dozen hydrogens, how many dozen oxygen? 1 dozen oxygen, how many dozen waters would I form? Molecules of water. 2 dozen. And so it doesn't have to be individual molecules. This would be individual molecules here. I take 2 hydrogen molecules, 1 oxygen molecule to form 2 water molecules. The same balanced chemical equation can be interpreted as dozens here. And so if I take 2 dozen hydrogens, I combine it with 1 dozen oxygens, I'm going to form 2 dozen waters. But if I'm working with dozens, or if I'm working with individual water molecules, then I have to worry about what? Like for example, you know, the average water molecule weighs, you know what the average water molecule weighs? 18.02 U. But am I going to find a water molecule that weighs 18.02 U? Why not? Because that's the average of all the isotopes. All the same thing with hydrogen. You know, the average mass of an oxygen molecule is 32.00 U. But are there any oxygen molecules in nature that weigh 32.00 U? There aren't. Because that's an average of, yeah. And so how many different oxygen molecules occur in nature? We can have 1616, 1617, 1618, 17, 1718. You know, we figure them all out, right? And so there are a lot of different ones. So if we're working at the particulate level, then we care about what isotopes we have. Is this an H1H1, H1H2, H2H2? What is it? You know, we need to know. Because it makes a difference. It makes a difference. But do we work at the particulate level? No. In fact, we don't even work at the dozen. We work at the mole level. And so if I have a mole, and I got this wrong last time. What did I call a mole? I've been calling it 602 million trillion. I miscounted. It's 602 billion trillion. And so we're usually working at the mole level. So this would be 2 moles of hydrogen, not 2 dozen, not 2 individual. This would be 2 moles of hydrogen. 2 moles of hydrogen, that would be 1,200, no, 12, what would it be, 600 billion trillion? This would be 1,200 billion trillion molecules. With 1,200 billion trillion hydrogen molecules, are you going to worry about what individual ones are? No, you just want the average. So the average would be it's 1.08 times 2, which would be 2.016. So the average hydrogen weighs 2.016 U. But we have a mole of them. And so how much does a mole weigh? A mole would weigh 2.016 grams. And we have 2 moles. So if we have 2 moles, we're talking about 4 grams of hydrogen. And then 1 mole of oxygen, 32 grams, forms 2 moles of water, which would be 36 grams of water. And so we would typically think at the macroscopic level. When we're dealing at the particulate level, then we've got to worry about the isotopes. If we're dealing at the macroscopic level, we'll just take the average. It's fine. And so that goes back to this slide. At the molar level, we read the coefficients differently. At the particulate level, this is 2 molecules of hydrogen, 1 molecule of O2 forms 2 molecules of water. A lot of people don't like fractions. A lot of people, you can't read this at the particulate level, because if you read this at the particulate level, this would say 1 hydrogen molecule plus 1/2 an oxygen molecule. Can we have 1/2 of an oxygen molecule? No. But if this were at the mole level, then fractions are no problem. You know, or even at the dozen level. Could we have 1 dozen? Yeah. Could we have half a dozen? Does half a dozen exist? Sure, it would be 6, right? At the mole level, it's no problem. 1 mole, half a mole, doesn't matter. 1/4 of a mole, 1/10 of a mole, it's fine. Oftentimes you'll see fractions when we're interested in water. You know, is this reaction endothermic or exothermic? It's exothermic. How much heat is produced? Well, it depends on how much water is formed. If you form 2 moles of water versus 1 mole of water, you're going to form twice as much heat. You know, it's like if you try to melt 1 pound of ice versus melting 2 pounds of ice, is it going to take the same amount of heat to melt 2 pounds of ice? No. It's going to take a certain amount of heat, and you got to use twice as much heat if you have twice as much ice. And so if we're going to say, okay, it's going to take this much heat to melt ice, how should we say it? Should we say it's going to take this much heat to melt 2 pounds of ice? Or should we say it's going to take this much heat to melt every pound of ice, or 1 pound of ice? Typically, people are going to say, well, I want to know per pound how much heat. When you go to buy, well, I don't know about supermarkets nowadays, because now everything's 2. You got to buy 2 of them, or at least it gives you the impression that you have to buy 2 of them. Well, I don't want to buy 2 of them. I just want to buy 1 of them, right? This is the price for 2 of them. I want the price for 1 of them. Right? Well, this is it. This is like going to the supermarket. You have to buy 2 of them. So we got to buy 2 waters to get that heat. Versus, well, if you don't want 2 waters, you just want 1 water, this is it. Well, if we want only 1 water, then we have to deal with fractions. And so an important quantity is the amount of heat that's generated here. And when we state the amount of heat, we say per mole of water formed, not per 2 moles. How much heat per mole? And so if we're doing per mole, then we got to have fractions here. And So fractions sometimes are mandatory based on the way we think about energy. You know? Because this is not as convenient. You know? It's the same reaction, but we're going to get different amounts of heat. All right, that's this is where I'm going to leave chapter 8. And chapter 8 goes into combination reactions, decomposition reactions, single replacement reactions, double replacement reactions, and then ends. Then chapter 9. Chapter 9 goes through the solutions there. Then goes on. And so what I want to do here is I'm going to jump from chapter 8 to chapter 9 right now. Because what we're going to do is we're going to look at this reaction here. We can ignore the slides here because actually I need to go into the supplement here. But what we want to do is we want to visualize the structure. And so solid sodium metal, the element, does it form molecules? Does it form gaseous atoms? When you visualize sodium, what is the structure that you see? A lattice. And we call that lattice well, it's a lattice of sodium atoms, right? Something like this. And is that an ionic lattice? Covalent lattice? Metallic lattice? This is a lattice of sodium atoms here. And this is called a metallic lattice. This is made of metal atoms. This is what we visualize here. So if we visualize this at the particular level, then we just have two atoms here. At the microscopic level, we are visualizing what? 2 moles of atoms. How many atoms is that? Well, 1 mole of atoms is 602 billion trillion atoms. 2 moles would be 600 going to 1200. 1200 billion trillion sodium atoms. Now, do those atoms form molecules? No, so we represent this as an empirical formula. Yeah, these crystals have no beginning, no end. You probably have lots of crystals. Sodium. That's sodium. And then plus water. When you visualize liquid water, we need 2 of these. 2 moles of liquid water is what? 2 moles of liquid water would be how many water molecules? 1,200 billion trillion atoms, or 1,200 billion trillion water molecules? Water molecules. And so, you know, and I showed you some animations for water. Do you guys remember those? Pretty much? You know, liquid water is going to just have a whole bunch of water molecules. And these water molecules are going to be in motion. And so it's just liquid. You visualize that. 1,200 billion trillion. Well, we know about how much that weighs. You know, if I have 2 moles of water, you know, how much does that weigh? What does 1 mole of water weigh? I did this yesterday. 18.02. Therefore, 2 moles of water is going to weigh 36.04 grams. 36.04 grams is how many milliliters? Yeah, 36 milliliters. That's because we know the density. What's the density of water? Yeah, 1.0 grams. Anyway, for sodium, it's 20, what is sodium? 20, 22, 23? 23.00. 23.00 grams per mole. We got 2 moles. It's going to be 46.00 grams. And so we're going to have about 46 grams of sodium metal and 36 grams of water. Yeah. And this is going to form, well, 46 grams of sodium metal. Sodium is not the most dense metal. It should sink in water. This is going to be less than 46 milliliters. Then we're going to have hydrogen, H2. 1 mole of hydrogen. 1 mole of hydrogen is going to have 602 billion trillion hydrogen molecules, gas phase. And so this is, but it's not going to weigh much. How much is it going to weigh? 2.016 grams. And the volume is going to be quite big. You know, this is going to be 36 milliliters, but this is going to be about 25 liters. At 1 bar pressure, 25 degrees C. We're going to come back to gases again, so that we'll be able to figure out when we come back to gases. And then we're going to have 2 sodium hydroxides. Sodium hydroxide is AQ. Sodium hydroxide, what is that? Well, that's what we call a salt. Sodium hydroxide is a salt. A salt is like an ionic compound that's not an acid. It's not an acid, it's typically called that a salt. Pure sodium hydroxide, what would you expect it to be? Most salts in pure form are solids, liquids, or gases, or aqueous. Are solids, yeah. And so pure sodium hydroxide is a solid. In fact, I saw some pure sodium hydroxide the other day. I went to Orchard to buy some sodium hydroxide. You know what section I was in to buy some sodium hydroxide? The plumbing section. Because do you know what another name for sodium hydroxide is? It's another name for sodium hydroxide is drain cleaner. It's a lie. You know? In fact, they sold Red Devil Lye. Red Devil Lye is like sodium hydroxide in there. Sodium hydroxide is a white solid like this. And it's a drain cleaner because you put it in there, and the sodium hydroxide, you know, if there's oil clogging your drain, what it does is it, you know, breaks the oil molecules apart. It can do that. It breaks fats apart. In fact, you know, this is how they make soap. You know, they can make soap by if you take fat and something like sodium hydroxide, you can make soaps. So it converts the fats into soap, breaking apart the fat molecules. Well, that'll clean the drains as well. So I bought some sodium hydroxide drain cleaner. But what we say is that the sodium hydroxide is water soluble. That means, you know, it will dissolve in water. just like sodium chloride. Sodium chloride is water soluble, so we can make aqueous sodium chloride, salt water. Sodium hydroxide is water soluble, so we can make aqueous sodium hydroxide. But when we think about sodium hydroxide, solid, what type of structure do you expect it to have? Does sodium hydroxide form molecules? Form gaseous atoms, or does it form gaseous molecules? Or lattice? What do you think? Lattice. This is potassium hydroxide, but it's close enough. And so it forms a lattice like this. Do you see any molecules of, call it sodium hydroxide. Do you see any molecules of sodium hydroxide here? No. And so what we use to represent sodium hydroxide is called the molecular formula or the empirical formula. Empirical formula. So there's no real beginning or end. Like, for example, this and this. You know, which one do you think is the sodium? Which one do you think is hydroxide? This is actually potassium hydroxide. I thought it looked funny because sodium is a little bit smaller. Potassium is a little bigger. But it's okay. Potassium hydroxide, sodium hydroxide. They look very similar. And they have the same structure. But which one's the potassium? Which one's the hydroxide? Sodium. This would be the sodium. This would be the hydroxide. Now, if I look at it, you know, are they paired? Like this one paired with this one, or is it this one paired with this one, or is it this one paired with that one? You can't tell, can you? That's because it doesn't form discrete molecules. And therefore, this is an ionic lattice structure. And so we're going to just use the simplest unit. Now, what happens if you take the sodium hydroxide and dissolve it in water? Will it dissolve in water? Well, we ask ourselves, is it soluble in water? And so when we look at dissolving, let's take a look. There's not a good simulation here. So what we're going to do is we're going to look at sodium chloride. Is sodium chloride, will it dissolve in water? Table salt? Yeah. And so here's a small crystal of sodium chloride here. And if you take that small crystal, and this is water, right? Put it in water, what happens? It's water. This is slowed way down, so this is super slow motion here. In fact, I'd like to speed it up because it's so slow. Looks like nothing's happening. Huh? Looks like maybe it's not soluble. Okay, but something did happen. Did you see that? Look up here. Did you see that blue one? This green one broke off here. Do you see that? And so what's happening is the water molecules are kind of plucking apart the crystal lattice here. The blue one here, another blue one, green one, green one. And so the water molecules are basically taking apart the lattice. And what's happening are the ions are becoming dissolved in water. Do you see any molecules of sodium hydroxide that form there? No. And so the same thing is going to happen here with this salt. And therefore, I expect this to be a nice lattice type structure. And we take that lattice and then we dissolve it in water. Now, if I just added 36 milliliters of water, then what happens to all that water? Do I have any water left over? If I add 36 milliliters of water, would I have any water left over? No, all that water gets converted into, what happened? The hydrogens in this water get converted into hydrogen, gas, and hydroxide. The oxygen in the water gets converted into hydroxide. So if I started off with 36 milliliters of water, there would be no more water left. And so what I'm going to do is this. I'm going to add excess water. Excess water means that I'm going to have extra water in there. And so plus excess H2O. You know why? because I don't want any leftover sodium. You know, what would you rather have? Would you rather have leftover sodium, or would you rather have leftover water? Which one would be less dangerous to have left over? Water. And so leftover, if we have extra water, no big deal. Just let it evaporate if you want. But if you have leftover sodium, what do? One time I had some leftover sodium, so I had to dispose of it. And so you know what I did with it? I had a pool of water in the sink, so I threw it into the sink. And then it backfired, because what happened was it turned into molten fireball. This molten fireball shot out and landed on my arm and caused some burns. So it was like, what do they call that? Those videos. Well, anyway, so that was a big problem. So we don't want any leftover sodium, but if we have leftover water, no big deal. Now, if we have leftover water, what can happen is this sodium hydroxide that's formed will dissolve in the water. When it dissolves in the water, what is the water going to do? The water is going to tear apart the lattice, and it's going to make ions that are floating around in the water. These ions, are they floating around as pairs or molecules? No, they're just individual ions floating around in the water. Does that make sense? And so this is what we call sodium hydroxide aqueous. Let's say I just have 1 drop of excess water. You know, 1 drop is not that much, right? Probably not enough. Probably need a lot more than 1 drop of excess water, but you know, that's all it takes to be in excess, 1 drop. Actually, let's just do a side calculation here. As far as the side calculation, how many water molecules are there in 1 drop of water? So 1 drop of H2O equals how many molecules? If I had 1 drop of water, would I start worrying about what isotope I have, and it's heavy water or lighter water? And so I would have to do that calculation, but I haven't handed back your experiment 2. If I gave you back your experiment 2, you have that number written, and that is the volume of 1 drop of water. Does anybody remember that? Probably not, but I think I looked at most people got around 0.04 to 0.05, you know, plus some were like 0.03, some were at 0.02, some were higher. But the number that's usually taken is this. For water, we're going to assume it's 0.05 milliliters is equivalent to 1 drop of water. Some liquids have smaller drops, some liquids have bigger drops, like syrup. You know, syrup would have bigger drops. Ammonia solutions would have smaller drops. And so the drop size depends on what the liquid is. And so this would just be a dimensional analysis. So when we're adding the excess water, you know, let's add 1 drop of excess water. How many molecules are there? So if we do 1 drop of H2O, then we've got to get rid of the drops. So what's the conversion factor we could use? 1 drop is equivalent to 0.05 milliliters. So the drops canceled, and that gives me 0.05 milliliters of water. Now I've got to get rid of milliliters of water. What can I use here? I can go from milliliters to liters, or I can go from milliliters to grams, but that would be only for water. And so it turns out there's 1.0 grams of water for every 1 milliliter of water. That's called the density of water. So that would cancel. Now I have grams of water. Well, I need to get rid of grams. Where can I go from grams? I can go from grams to milligrams, grams to micrograms, grams to pounds. Where should I go? To none of those. I should go from grams to something new. I should go from grams to moles. And so it's going to be 18.02 grams for every mole of water molecules. So 18.02 grams of water for every 602 billion trillion water molecules. And so what does this come out to? Well, I only got one sig fig, so this is going to get out to 1.6 times 10 to the 23rd H2O molecules. And so what is this? This would be 160 billion trillion water molecules. 160 billion trillion H2O molecules per drop in a drop. That's a lot of water molecules, but that might not be enough to dissolve all the sodium hydroxide that's present, because there's a lot of sodium hydroxide. So usually when we add excess water, it's quite a lot of excess water, not just one drop. And it also depends on something called solubility, but we'll talk about solubility next. So we'll take a break for right now. And then